last afternoon of the meeting. I'm very pleased to introduce Dunfield, who will be introducing a bright new version of SnapPy polished last night. So all of you who have SnapPy will want to update it through the talk, I'm sure.
All right, well, thank you, Walter. So I should start by thanking the organizers for the privilege of addressing this memorial conference for Bill. As you know, computer experiment both by him and those done by others informed his work throughout his career, from his work on geometric structures to some of his last projects that we have heard about during this conference, and Kurt will tell us more about in the next talk. So what I'd like to do today is show you the program SnapPy, which is a program for studying the topology and geometry of three manifolds. Its philosophy follows the ideas introduced by Thurston in his notes, in particular studying hyperbolic structures on manifolds with cusps via ideal triangulations and parameterizing them by complex numbers and gluing equations. Because in the interest of time, I want to spend as much time as possible actually showing you how to do things. I'm not going to say anything really about the theory about how the program works. And in addition, like when I want to refer to some paper or some piece of software, it's kind of hard to do if I have something in front of me that I'm fiddling with. So I made a little page here at this URL, which has sort of an outline for the talk, in addition to one of my favorite Bill quotes. So this will just be things that you'll see in the course of this. So if I mention something like a paper or whatever, then hopefully it's listed here. Are we good, Dylan?
Yes, yes.
All right. Whoops. Sorry, I just want to kill the full slides. OK, so the program SnapPy that I'm going to be telling you about it's a free open source piece of software. You can get it from our website, which, of course, I turned off the lights just before I give the URL. But anyway, I'm going to just spend most of the time showing you this program. So I'm going to be showing it to you here on my Mac laptop, but it's also available for Windows and Linux, and it works essentially the same on those other platforms. So let me just start by starting the program up. And here we see the basic window. And, well, as you can see from that flashing little cursor there, this is some kind of command line-based interface. And like all such interfaces, it has certain drawbacks, which are, if you've never encountered this program before, what are you supposed to do? So, and even if you have used it before, of course, you've forgotten whatever command you were supposed to type. So I want to start just by, from very basics, assuming you've never seen this before, I'd like to tell you the three things that you should know in order to get around this blinking cursor of unknowingness. So the first is there is documentation on our website. It's also included in the help menu on the application. And there's a whole bunch of different things. Of course, who wants to read them? No one wants to read them. If you don't want to read them but want to watch them, there's also videos on YouTube that show various features of this, similar to what I'm going to do today. But anyway, that's documentation. No one reads documentation, we understand. So really the two things you need to know are the question mark operation and tab completion. So there is just one thing here on this first page which tells us something we could do. It says type manifold question mark to get started. So I'll at least read that much of the instructions. And when I do that, it prints out the documentation for manifold. It says a manifold is a triangulation together with a geometric structure. And then there's more words I don't read. The thing you want to look for in each of these little snippets of documentation associated with manifolds and fundamental groups and whatnot are these examples, these things indicated by a excess of inequality signs. These are examples of the thing in question being used. So let's just go ahead and start by go ahead and trying this. So if I'd read a little more in the documentation, well, I guess it's still up there at the top, by doing this, what I'm getting is loading a link exterior from the Rolfson table. So this is the 42nd 9-crossing knot by his scheme. And then the other thing that the example code that scrolled off the top showed you was you could compute the volume. This is a hyperbolic manifold. It has a complete hyperbolic metric of finite volume. And that volume is approximately 4.0568, whatever. All right. OK, well, that was good. We were able to create a manifold. But now, again, we don't know what to do. So we know we can compute the volume of a manifold. And presumably, there are many other things that we could do to it. And the way we find those out is to use tab completion. So if I just type m a period and then hit the tab key, it prints out all the things that we can do to this manifold. So it looks like we can do a Dane filling. We can drill stuff out. We can compute its homologies. There's a whole bunch of things. So many, maybe I'll just look at those that start with the letter C. So for instance, there's a complex volume. Well, OK, so I was able to use that in an analogy to the ordinary volume function. But you might be wondering, well, what is the imaginary part of that complex volume represent? It's the kind of thing you might want to look up in the documentation, which we can always access using this question mark operator. So we're going to sort of interrogate the complex volume function. And it tells us, conveniently, that the complex volume is the imaginary part is twice pi squared times the Chern-Simons invariant. So this thing where you have some object on the command line, you manipulate it by using tab completion to find out what you can do to it, and then by using the question mark operation to interrogate it to find out what exactly those things do. This is the way that this interface is designed to work, and allows us to have both the power of a command line interface. I'll illustrate this later by sampling, showing how to go through big numbers of manifolds and select those with particular properties, but still allow us to sort of interact with manifolds on a one-to-one personal level.
5 sub 2 is not an amphichiral knot.
The knot 5 sub 2 is not amphichiral, yes. And its Chern-Simons invariant is non-zero. Yes, that is the knot 5 sub 2. Yes, so that things that look like 5 sub 2 or 9 sub 42, those are knots in the Rolfson table. As you point out, that's not an amphichiral knot, which is certainly can be seen from the fact that Chern-Simons invariant is non-zero.
Can we see the projection of these knots?
Yes, absolutely. So there is, let me show you maybe it's the most important command, the browse command. So this allows us to see a bunch of information, including what was just requested, the link projection. So this just brings up a table of many of the basic properties of the manifold. Here in particular is the link, 942. And I guess some of these we've seen already. There's the volume, the Chern-Simons invariant, a homology is boring, it's a knot exterior. It's a presentation for the fundamental group. I guess after the volume, one of the most basic invariants of a hyperbolic manifold is the length of its shortest geodesic. That's indicated here. That looks like there's only 2 geodesics of length less than 1.0. Maybe we should increase that. See if there's. Look at geodesics up to length 2. There's several more. There's also a little box down here, which is pretty useful. This is the also known as box. So SnapPy comes with almost 2 million manifolds included right there in the box. And about 250,000 of those it knows really well. And it can very rapidly tell you if any manifold that you've constructed is one of those in its table. So this box at the bottom, this lists all the different tables in which this manifold appears. It appears as a knot in the Rolfson table. It appears in a census of manifolds that are made from at most 5 ideal tetrahedra. It's the 4th non-alternating 9-crossing knot in the Haas-Thistlethwaite-Weeks census. And it's also a small number of tetrahedral knot exterior in S3. Right? So this is the browse method. This is like the most important of all the things that you can do to the manifold. It's the most important because it gets you most of the stuff right up there in front of you without any more typing. So I think we should have a pretty picture. It's after lunch. So here's the Dirichlet domain for this hyperbolic manifold. Michel Boulot's talk, he was mentioning symmetry groups of knots. SnapPy can compute those as well. This one is just Z mod 2. I guess he was also talking about integral homology spheres. Maybe let's just, for fun then, create an integral homology sphere. We can also use this pane to do a Dane filling. So that corresponds then to Dane's surgery on this knot. If we do 1-1 Dane filling, we get another new manifold. So now it's first homology 0. It's an integral homology sphere. Its volume has gone down as it must. Chern-Simons invariant has switched around. Oh, yeah, let's look at the Dirichlet region here. So now that we've made it compact, of course, the Dirichlet domain no longer goes off to infinity like it did before.
Can you go back to the before unfilling?
Before unfilling it. Sure, absolutely.
So what is same increment no? Does this AKA?
Yes.
What is the no?
Oh, OK, so this same link complement. So this doesn't really make much sense in this case because this is a closed manifold. So SnapPy, when it has a manifold with cusps, you're sort of thinking, maybe it's like a knot exterior in S3. So there's, along that torus cusp, there's sort of a preferred meridian and preferred longitude. So if I had two manifolds, you could ask, well, are they both the same topologically? And also the meridian over here and the meridian over here, are they the same? And that's what that last column is telling us. In the case of a closed manifold, it's kind of meaningless. These numbers guaranteed to be exact? No, these numbers are not guaranteed to be exact. SnapPy works using floating point numbers, standard precision. Floating point numbers, 53 bits, 16 digits, roughly decimal digits. I'll show you later some ability to compute these things to higher precision, including, in the end, arbitrary precision, a little later in the talk.
What does that mean? There's a remain here, but is it exact to a certain number of places?
It is likely exact to all the places that you see, but the program does not guarantee that.
What does it mean for a complex number to be the length of a geodesic?
So if you have a geodesic in a hyperbolic 3 manifold, it has both a length, but then as you walk along that geodesic, when you come back, there's like a holonomy, there's a twist. And the imaginary part is the thing that's describing the angle of that twist. So these numbers here will never be more than plus or minus pi because of that.
When you say length cutoff 0.0, they get the value of those complex.
Well, so this part here, this is the ordinary length, the length of the real length of the geodesic, just the length of the circular loop. This part here is additional information describing the holonomy as you go around.
So the length cutoff just ignores the imaginary
part. The length cutoff just completely ignores the imaginary part, because that's sort of just additional information about the geodesic. Are there other questions? All right, so OK, so let's maybe go back to the original thing. I'll go ahead and unfill this cusp. Another thing that we can do to modify a manifold, we're filling it in, adding in a solid torus. Well, of course, we could punch one out. So let's take the shortest geodesic in this, the systole. You might remember from Alan's talk, because this is a knot complement in S3, the length of this systole can't be very long. This one's only 0.43 hyperbolic units. So we drill this thing out. We get a new manifold. Now it has 2 cusps. And, well, of course, what we did is we took a knot exterior in S3 and we drilled out a simple closed curve. So this is now some 2 corresponds to the exterior of some 2-component link. And SnapPy immediately recognizes that it's the, in the Rolfson table, it's the first 7-crossing link in the table, which is also the 6th alternating one in some other table. OK, so let me maybe just bring up a picture of that link. So to do that, I'll go back over here to the command window. All the information that you see in these browsers, of course, available also at the command line. Let me first just bring up a copy of this link so we can see a picture. All right, so there's our two-component link. Both components are obviously unknotted. So maybe this is the kind of problem you might want to solve with SnapPy. Maybe you're interested in, there has to be some Dane surgery on this blue component which turns the red component into the knot 942 that we had before. So let's say we wanted to figure out what Dane surgery that is. So we could take our original manifold M, that's the exterior to 942, we'll drill it out. So again, the number 0 there is which curve we wanted the systole, the shortest. Let's just double check that these things really are the same. 0 means the shortest curve. So the convention here is that things are numbered from 0. The first cusp is cusp 0. The second cusp is cusp 1. It's the C convention, not the Pascal convention. So just check and make sure they're isometric. Good. But we need more. To figure out the Dane surgery coefficient, we need more information. We want to know what happens. So when we drilled out the first thing, we had two cusps. And I realize now, oops, I have two cusps. One of which will correspond to this blue curve, one of which will correspond to the red curve. And we need to know sort of what happens to a meridian curve on the drilled out thing. The meridian curve corresponds to the thing you fill in to get 942. We don't know where that goes on the boundary torus here. Some number of meridians and some number of longitudes. So if we want, we can ask for more information, not just that it's isometric, but what does the isometry do to the cusps? So if we look here down here at the bottom, there's an isometry that takes cusp 0 to cusp 0, cusp 1 to cusp 1, and then it acts. So we have to describe then two homeomorphisms of a torus to another torus. We can do that by a matrix here in GL2Z. In particular, the meridian on the manifold D, that's the thing that we got by drilling out. The meridian on D goes to this vector here, 1 meridian plus 1 longitude of the knot exterior. So that says, then if I go back to N, which is my 721 exterior, and I do a Dane filling. Yes?
So where is that line? D doesn't make it to N true. So why you add that true to juice?
Oh, right. Well, of course, see, I should have shown you the documentation, right? So he asked, why did putting true cause it to spit out this additional bit of useful information? Well, if I look at my documentation, again, don't read the documentation. Never want to do that. You just want to look at the examples. Right? So here's an example where somebody has the 5. That's the Whitehead link, I guess. And then there's some other manifold. And then, OK, it's showing you how to actually get the isometries that map M to N. And so you do it by saying return isometries equal 2. And if you were lazy like me, you don't have to say.
A matrix, like 1, 2, 0, 1 minus 1, is that a matrix?
Yes. Yes. These are matrices. This is the matrix that's describing the homeomorphism from cusp 0 of the manifold M to cusp 1 of the manifold N. Right? So they're two tori. They have preferred peripheral framings. There's a matrix describing that homeomorphism. All right, so OK, right. So what we figured out was that it was going to be the 1-1 filling. So we'll do 1-1 filling, and I have to tell it which cusp I want to Dane fill. OK, and let's see if I got this right. M was our original manifold 942. And N was the Dane filling on this link. And so we found that if we do 1 plus 1 Dane filling on the blue thing, we turn the red thing into 942. All More questions? Oh, how do you know which one is red and which one is blue? So up here in the browser, the colors are supposed to match. So red is cusp 0, and blue is cusp 1.
Push drill. That was really linked out.
No, this is already, so it's already been drilled out. So the object that SnapPy is working with is basically a hyperbolic manifold with cusps.
So we can look at the Dirichlet region.
We can look at the Dirichlet region for this.
With cusps. Yeah.
So it's got 2 cusps, and in this case, the Dirichlet domain has 2 things. We can also, I should have shown you this pretty picture earlier. You could also, I filled one of these things in. Let me not. There we go. OK, so here's the Dirichlet domain for the actual 2-component link exterior.
So what's the center of that Dirichlet domain?
What do you mean, what is the center?
What is the base?
Oh, well, so it picks a point, and it builds a Dirichlet domain, and then it moves that until the injectivity radius at the point you're using to make your Dirichlet domain is locally maximal. So it tries to pick, so as Kurt's pointing out, to make a Dirichlet domain, you have your discrete group. You have to pick some point. Which point should you pick? This tries to pick a point which makes the Dirichlet domain look as fat as possible.
So it's possible that you must look at the same manifold and SnapPy.
Oh, absolutely, absolutely. And in fact, if you want, you could actually specify how you would like it to choose the base point for the Dirichlet domain. There are several options available to you there. You could also, if you like, so we had this, to go back to Ilya's question, there's the red and the blue corresponding to the 2 components or corresponding to the 2 cusps. We can also think about little neighborhoods of those cusps. So those are tori. Yes?
I was just wondering what sort of invariants are, but that's not on topic. So.
The invariants of what?
Well, under the invariance tab, is that like very still?
Oh, no. The invariance tab is just the initial tab that you have in the start. So volume, homology, fundamental group, length spectra, things like that. Dave?
Following up on Kurt's question, does SnapPy have the ability to attempt to find the global maximum of injectivity radius?
No, not built in, no. I mean, you could, I think you could specify different starting points and then sort of try to search to find a global maximum. But it doesn't have, you can't just say, give me the global maximum. Sorry, did you have a further question?
Oh, does it compute things like that? Like, say, the very field?
It has some ability to do that, and I will show that a little later in the talk, absolutely. Yes?
To what extent does the representations of the links vary? Like, will it always look the same, or it'll look different?
For
like the same thing, like it'll always compute it to be the same? Like, it'll look the same?
Oh, you mean like this picture? The links. So more or less, yes. I mean, there's some, it just stores the link purely combinatorially. So, and then to make a picture, it has to choose some representation. I think there's a small amount of randomness in that. So there might be a couple pictures, like maybe you get this thing rotated or something. But it'll always be topologically the same projection. So you could also, so you have these 2 cusps, and so you could, if you want, you could stand on one of the cusps and look into the manifold. And so as you learn from the not video, when you can see forever in a compact or finite volume manifold, what you see appears to you to be the universal cover of the manifold. So here I am standing on the red cusp, looking into the manifold. So I see the red cusp where I'm standing many times. Let me turn off. There's kind of a lot of information there. Let me just turn off some of it. You look into the manifold. You see the red cusp where you're standing many times. You see the other cusp, the blue cusp, also many times. That sort of purple parallelogram, that's a fundamental domain for that cusp. So the cusp is Euclidean with the geometry identify that side with that side and the top to the bottom. Of course, these cusps, they're not unique or something. They make them bigger or smaller up to a certain point. So I could make the red cusp, I moved it out sort of towards infinity. I could then make the blue cusp bigger.
So these are horospheres?
Yeah, these are horospheres, exactly. Exactly. So downstairs in the manifold, each one of these horospheres has a stabilizer, which is z plus z, and it's quotienting down to a torus, which you can think about sort of running along the link. So you can adjust the sizes of these things We could switch. What does it look like from the blue side? That's what it looks like from the blue side. Of course, it has to stop drawing these horospheres at some stage. There's so many of them. By so many, I mean infinite. We could ask it to plot a few more. OK, so that's some basic examples using a link, a couple of links that we drew from the tables that come with SnapPy. You could also make your own free-form links. Like maybe you're interested in the Whitehead link that came up in. Oops. That's not good. All right, that's just not good. I should. OK, well, sorry about that. This is work in progress. All right, well, that's just not working, period. OK, give me 1 second. The part of that quote I had up at the beginning by Bill about computers programming being 2 orders of magnitude more precise than typical mathematical proof, there was part of it I deleted, which is about how any program, no matter how, any large program, no matter how well tested, has bugs. OK. Apparently, I just managed to illustrate that. So we can also, actually, let me call this W, just give it a name. So if we want to make the Whitehead link from Alan's talk, if we just ask to create a manifold and don't tell it a name, then it presumes, well, you're going to have to draw it, because how else, if you didn't provide it any information, provided a file or a name from some census, then we're just going to have to come up with something. Let's see. So I want to switch this one, and that one, I think. So now I've drawn my link here, and then to get it back into SnapPy, I need to go to the Tools menu and select Send to SnapPy to send it back to the blue window. And we can, for instance, compute its volume. So the volume is made out of one regular ideal octahedron. The link editor has a number of other features. So like if you, this is sort of, it's, initially you're drawing these things using sticks, which is natural, but maybe not aesthetically pleasing. So if you want, you can round off all the corners. That doesn't, to me, look very aesthetically pleasing. So there's actually, if we want, we can edit it in the smooth mode. I don't really know if I'm making progress here, but. And then, oops. And then if we want, we can go back to this mode. And in any of the modes, you can export these not pictures. Of course, you can save them in a format that SnapPy can read them again. But you can also export them in PostScript or SVG or PDF. So if you want to edit it in Inkscape or Adobe Illustrator, you can also export it as TXT macros if you want to put those into your LaTeX file. So you can use it to make a quick picture, for a paper or something. You can also edit a link associated with one of the things from the table. So let me go back to the manifold 942. And if I do m.plink, plink is the name for our link editor. It's supposed to be like PL or something like that. Brings up our link. So maybe let's say we were trying to figure out the unknotting number of this link, which since it only has 9 crossing, it's almost certainly 1. So can someone suggest a crossing here I should change in order to unknot this knot? Danny? Which one? This one? OK, let's try that. All right, so I'll go over here, and I'll just click on it to swap that crossing. Hello, computer. There we go. What? Did it not swap? is not liking me for some reason. I want to try this again. There we go. So, OK, I undid that. That seems a promising suggestion. Let's send it over to SnapPy. It's received a new triangulation. It's very excited. I asked for the volume. It says, well, OK, it says basically 0. Right? So SnapPy's default assumption is that most manifolds are hyperbolic. And if they're not, it's really not going to tell you anything about them anyway. And so if you feed it something non-hyperbolic, it will try to somehow find a hyperbolic structure, but will fail. And so finding something with volume 0 is one way to fail. Just to make sure, though, we could ask what the fundamental group of this is. And we see that it's a fundamental group with one generator and no relator. So in other words, it's Z. So it really is the unknot. So congratulations to those who pointed out the correct way to unknot this knot. Now, you can also create knots and links sort of more programmatically. So by which I mean, like, let's say you wanted to look at the -237 pretzel knot. So that's one of the first examples of a knot in S3 that had non-trivial cyclic surgeries. And of course, you could sit there and draw it, but you'd have to count like up to 7, which I find personally difficult. Instead, you could try to specify the knot using kind of the language of tangles, of rational tangles. So that's one of the things that SnapPy knows about. So we could take the -1/2 tangle, the 1/3 tangle, and the 1/7 tangle. And then there's various operations on tangles, like addition of tangles is you set the two tangles next to each other. Multiplication is you stack them vertically, like you're making a braid. So I'm making a pretzel knot, so I should add them together. And let me just move this up slightly.
In addition to any number of arguments. In addition to any number of arguments.
Yeah, you can add as many things as you want. It doesn't care. And then you have to close up this tangle to make a knot. And I think what I want, if I remember correctly, is the numerator closure. So this is a link. It has 12 crossings. We could look at a picture of it if we want. I'll let you try to untangle that in your mind, the -237 pretzel. I can then take the exterior of this link. That's a hyperbolic manifold. I can ask it to be identified. So in particular, it tells, if you're aficionado, you recognize at least one of those as the -237 pretzel. Yes, Kurt. Can it figure out this is a fiber link? Pretty much. So I'll show that actually. When I'm talking about SnapPy and Sage, remind me if I don't remember. And I will demonstrate that it does know that. So I should say that this, so one of the more recent features I wanted to show off, we added this spherogram module, which allows you to create links sort of programmatically, either by just like taking a bunch of crossings and gluing them up, or by building things from tangles. You can add tangles, multiply them so you can build braids and plaits and so on. And this is probably as good a point as any to point out that you haven't noticed, hopefully, but, well, I don't know, hopefully. I have not yet mentioned that, in fact, I've been interacting with this command line, and I'm interacting with it in a language that's called Python. So it's very high-level, object-oriented, interpreted language. It's very popular in the real world and in applied mathematics. And so the advantage of the way we've set this up is that if you want to, you don't have to, but if you want to, you can do all sorts of programming. So let me, for example, you can write a little function that will build chain links. So these are things you make from little rigid chains, and then you have to put a certain number of twists in them. So I'm going to just copy that code over, paste it in. OK, and then I can create a link, twisted chain. It's a good exercise to try to figure out what each of these steps is doing. I should point out, actually, maybe before I do that, at the top of this, there is an important link to a page which summarizes the graphical conventions. In particular, it reminds you what all the tangle calculus moves are.
So can I ask a question about that?
Yes?
So at the very top corner of this page that you're currently on, right, everything is illustrated with two strands, but I mean a tangle can have
The tangle can have more strands, that's right, and it's cool with that.
So what's the 1 over t?
What's the 1 over t? OK, maybe that one, it only allows you to do that with a, yeah, so a tangle is actually something like this. So the 1 over t, it does have to have only 2 inputs and 2 outputs. But the others, it's happy with. Yeah, so, OK, so there's a bunch of operations, conventions. OK, so if I ask like this link, this is the twisted chain. What does it do? Well, I'll just show you the picture. So it builds this link, which has 10 components. The components are numbered actually up here in order to keep our color scheme straight. So you don't have to remember magenta is 4. So there's 10 components, and you sort of, each one's an unknot. It's kind of a rigid thing. And then at the end, to glue the first one up to the last one, there's this green thing coming around, and that has a certain number of twists, which I better hope is 7. It is. So that's an example of how you can create very complicated links relatively easily. So I guess so far I've been trying to focus on link exteriors, this being a very natural class of manifolds, but of course also a very special one. Another source of manifolds that comes with SnapPy is tables that people have made by just saying, well, let's say we start with maybe at most 9 tetrahedra, ideal tetrahedra, and we'll try all the possible ways from gluing them, and we'll just keep the ones that give us hyperbolic manifolds, cusp hyperbolic 3 manifolds. So Ben Burton had a recent paper on the archive where he produced a list of all the ones that have 9 tetrahedra. And those are now available in the version of the program that, as Walter mentioned, was released 14 hours ago in what's called the orientable cusp census. So it turns out there are 62,000 cusp hyperbolic manifolds that are made from assembling at most 9 tetrahedra. Let's just take one of them. I don't know which one. Maybe I'll just pick one at random. That's kind of a funny little name. This means orientable 9 tetrahedra, the 33,437th of its name. You know, and of course, 62,000 is a lot of manifolds. Maybe you feel intimidated by that. You just want to start with a few of them. You can look at subsets of these censuses quite easily. Like maybe I just want to look at the first 20 of them. So this is something in Python that says, given something that's basically a list, slice off the first 20 things. And maybe I should get some information about them. Like you might wonder how many tetrahedra are there in there. Right, so if you look at these, the first 20, the first 2 have 2 tetrahedra, the next few 3, the next so many 4. If you look at the ones at the end of the list, we could do that too. So these are the last 20. The last 20, of course, all have 9 tetrahedra. You can also do things like strip out samples by volume or by, like maybe let's say you want to look at ones that have 3 cusps in this census. And maybe for whatever reason you want those whose volume is between 6 and 7.5. I don't know why you'd want to do that, but it's, well, the reason I want to do that, that's a tight enough request. There aren't very many answers. So it turns out in this table of 62,000, here's all the 3 cusp manifolds whose volume are in that range.
Where's the syntax for that sort of restriction document?
So there is documentation. Now let's see, how do we access documentation? We use the question mark operator, and it gives a whole bunch of examples. In fact, this one seems to exist solely of examples, showing you how to use it. All right, so this thing here, first thing is an example of slicing by the index to give us everything between the 3rd, 4th, and 5th manifold. This one here, we're slicing by volume. It's also in the documentation for the censuses on the webpage.
No, it's the first thing.
So it knows because the first thing is those are integers and those are floating point numbers.
That's terrifying.
Some of us are not easily intimidated. There's also, I should say, like, there's not just cusp manifolds. That's what we looked at so far, except for that one integral homology sphere that we created by Dane surgery. So there is a census, the Hodgson-Weak census of closed orientable 3 manifolds that comes with this. And I mean, one of the nice things you can do in Python is it has what we would call set definitions as mathematicians or computer scientists would call the list comprehension. So we can do basically, give me the set of all manifolds in this for which there are, let's say, integral homology spheres. So m.homology.order is 1. So there's about 11,000 manifolds, so we better give it a second. I think we only need to give it 2 or 3. And it turns out that there are 150 of them. Maybe we're interested in the smallest volume one. Let's give us sort of the minimum one. I guess it probably, yeah, it's not smart enough to know what I mean when I say give me the minimum of a set of manifolds. I have to better tell it. So let's give me the minimum where I've sorted them by the key, which is their volume.
What's the meaning of lambda?
Lambda is, it creates a temporary function.
Why couldn't you use the name volume?
Because it's not the volume function, it's the volume method of this thing. So yeah, that's a little ugly, I admit. Other questions? So that's another important source, these manifolds built from a certain number of tetrahedra. I should maybe just point out, and it's a good segue to my next topic, this census here, the Haast-Thistlethwaite link exteriors, is the basic source of a much larger table than the Rolfson table. This has all knots and links through 14 crossings. And maybe let's just look at a 14 crossing. Randomly chosen 14 crossing link. Oh, looks like we drew from the pack a 3-component link. These are the Dane surgery coefficients. Currently, none of the cusps are filled. So it's a 3-component link. And maybe, I don't know, we're interested in its Dirichlet domain. Ooh, that's not good. It's unable to compute the Dirichlet domain. And this goes back to the question that Al was asking earlier about, are these things certified to be exact? Or, as I said, we're only sort of working with floating point numbers of a certain given precision. And consequently, there are some examples that are just too big for it to handle. I mean, hyperbolic space is highly dispersive. So as you try to start tiling stuff out, errors have a bad tendency to accumulate. So one of the new features that was added last year is the ability to work with manifolds at higher levels of precision. So if I ask to upgrade my manifold to a high precision manifold, let's just compare the volume here. And you can see that the answer that I got for the volume of H is much, much longer. And that's because the high precision manifolds are working with what are called quad doubles. So these are 4 ordinary doubles, or roughly 60 decimal digits of accuracy. And one thing about this, one of the things that this allows you to do is while with ordinary precision it's almost impossible to compute the Dirichlet domain for a typical 14 crossing knot, at this level of precision there's no issue whatsoever. So given that I chose this random, you're probably almost certainly all collectively the first people to ever see the Dirichlet domain of this particular manifold. Now, the question that, yes?
There's another census I know better, the HTL not census. Could you redo that huge project now, replicate it and verify it again, sort of using a small amount of code plus SnapPy?
I think presumably one could. I mean, somehow the thing that would be missing is you would need, yeah, you certainly, I suspect you would certainly do it easier with these tools than what they had to do. Yeah. So the question that I was asking, oh, Dave.
Is there a provable statement along the lines that if you keep adding precision, it will eventually be able to compute a Dirichlet domain, maybe even with a canonical base point?
Sure. I mean, it's certainly algorithmic that you can build a Dirichlet domain. I mean, in the proof that Casson and Manning gave, that you can decide if a manifold's hyperbolic in particular, you can do that. But still, it is a very common question I get. Sorry, yes?
Is there a hypothesis based on Burton's census for what the growth rate of the number of manifolds is as you keep adding?
Oh, the question is, what's the hypothesis for the growth rate? And the answer is it's exponential.
On any particular word?
Oh, I don't know that. I mean, any of these kind of things, whether you're counting knots or links or manifolds, I mean, you're always going to get exponential or super exponential growth. That puts a limit on how far we can ever go out in these censuses. You'll never see someone make a table of all 30 crossing knots. It's just there's too many of them for that to be a feasible task. So I did want to say that a question I often get is, well, are you sure this is really hyperbolic? And if that question is of interest to you, you should read this paper by Neil Hoffman, Hidetoshi Masai, and a bunch of numerical analysts who actually give an implementation of a provably exact method for deciding if a manifold is hyperbolic. So what it does is it computes the hyperbolic structure to very high precision, then uses an effective version of the inverse function theorem to certify that there's a solution to the Goulian equations nearby. And it gives you precise control on all of that. So this is not part of SnapPy, but proper. It's an add-on thing you have to install, but I hope it will be in the future. Our questions? Yes? Sorry, is it? No, so this is, yeah, so he's asking how do you install this under Linux. So we have detailed instructions on our web page, but it's not as easy as just saying apt get install SnapPy. If you say that, you will get a high-quality music player. Oh, he said claims to be high quality. I didn't actually try it. OK, so my next topic, I want to say just a little bit about using SnapPy with Sage. So Sage is an open source mathematical package. It's designed to let you do things that you might otherwise do in Maple or Mathematica or MATLAB or more specialized programs like Magma. And what distinguishes it, well, one is that it's free and open source. And the other thing that distinguishes it is very broad. I mean, it can make a plot for your calculus class, and it can also, compute some L function associated to some elliptic curve you defined over this there number field. And you can, of course, install it on your own computer. You can also use it online in the SageMath cloud, sign up for a free account. And the version of Sage that's inside the SageMath cloud includes SnapPy as a component. So let me go ahead just on my computer. I'll start Sage. So the thing is, Sage's underlying programming language is also Python. And so in the end, there's really takes no effort to, if we want, use SnapPy here. Like maybe we're going to, here's just a typical, let's just do a small one. 11 crossing knot. It's an inoffensive 11 crossing knot. We saw just before that you can compute things initially just a standard precision, then quad precision. But maybe you really want just incredibly silly amounts of precision. You can do that, unfortunately, right now only inside of Sage. Maybe we want the holonomy representation of the hyperbolic structure on this manifold to 10,000 bits, which is roughly 3,000 decimal places. Right? So what is this thing? So this is a representation of the fundamental group. Here's the fundamental group. It has 3 generators, 2 relators. And we could ask, I don't know, what does this representation do to the product of the 3 generators? Well, that answer is not very comprehensible because, of course, it involves a 4 by 4 matrix, each of which is complex, each of which has 3,000 digits. So let's just truncate the answer, pushing it down into ordinary precision. There's our matrix associated with that. OK. Another thing that you can do special in the Sage version, I just wanted to show you a couple things of that nature. Compute the Alexander polynomial. Well, the Alexander polynomial, that is 1. I mean, as Yini told us, reminded us that the Alexander polynomial gives you some control over the genus of the knot. In this case, it can't tell it from the unknot. But there are much more powerful Alexander polynomials that replace ordinary cohomology or homology with twisted coefficients. And as a member of the Thurston school, of course, the thing I want to twist by is the holonomial representation of the hyperbolic structure. Stefan Friedel and Nicholas Jackson and I wrote a paper about this. And that's one of the things you can compute here, is you can compute these so-called twisted Alexander polynomials. So if you do that, you get this polynomial, which appears to have degree 10. And if you unwind the bound on genus you get from these things, which depends on the dimension of the representation and whatnot, this is telling you that the genus of this knot is at least 3, which indeed it is. And in fact, in our paper, we computed these hyperbolic twisted Alexander or torsion polynomials for something like 350,000 knots. In every single case, the bound you got on the genus was, in fact, the correct answer. So at least experimentally, if you want to compute the genus, you just compute this thing. There are some other examples of things that you can do. There's some preliminary stuff for computing trace fields, things like that. That's in the documentation. I'm kind of running out of time, so let me not talk about that. You can do, well, I can't resist doing this one. They do belong. So these are just floating point approximations. If you want, it is capable, at least in this example, and we did this particular example in our paper, you can figure out what they are exactly. Exactly. You find out you guess the minimal polynomial based on the decimal expansion, and then yes, that's the thing that sort of thing was first done in the program Snap by Walter Neumann and Oliver Goodman. Actually, I really want to do this example, but I don't think I will because I don't have time. OK, so I wanted to say just a couple more things before spending a couple minutes speculating about what's next. You're supposed to remind me. Oh, right, fibered, yes. So right, so that manifold we were interested in was the -237 pretzel. This is one of its many names. Just as with the ordinary Alexander polynomial, these twisted Alexander polynomials provide an obstruction to fibering over the circle. So this example here, well, it obviously doesn't fiber. Its Alexander polynomial is 1. It's a hyperbolic manifold. But also, this polynomial here is not monic. 1 is not 4 something. Whereas here, this is the twisted Alexander polynomial of the -237. You can see it's monic. And again, experimentally, for the 300,000 odd manifolds we tested this on, this is a perfect test for whether it fibers. And I think we were so bold as to conjecture that. OK, so this is just one of many programs for exploring geometry and topology in dimension 3. I maintain a website called computop.org, which just has lists of programs here, a bunch of things, 2-dimensional, so like train tracks, like in Bess Mladen's talk. There's SnapPy, a bunch of variants. There's like purely things coming from normal surface theory. In particular, Ben Burton, with the Regina program, has made huge strides in actually effectively implementing Hawkins-style algorithms. You can take a small a reasonably small hyperbolic manifold and ask, is it Hawken? It can actually answer. I did never think that was actually possible, but it turns out it is. You can compute Haggard floor homology of various things. I mean, a project that I'm working on now involves sort of like, the nice thing about Sage is somehow you can do this all within Sage. And you can then work with something that maybe computes Haggard floor homology or Hawkenness or whatever, and you can try to explore these manifolds. So in my last couple minutes, let me just speculate a little bit about what's next. I mean, as we saw in the giant diagram Ian had up before, there's been a lot of progress in three-dimensional topology since I got my PhD sometime in the last millennia. And so many questions have been answered. I think that the field generally is going to move from somehow qualitative statements about do there exist, to quantitative statements how many, how quickly. And I think, hardly an expert, but it sort of seems to me that the older a field is, the more quantitative the questions. I mean, number theory is very old. We've known there are infinitely many primes. That's probably length of recorded history or something like that. And what is the Riemann hypothesis? It's about the error term in accounting theorem. So we're going to talk more about kind of quantitative questions, and I think there are a lot of interesting ones. One potential source of such questions are looking at random manifolds. I mean, I alluded to earlier that tabulation will hit a hard limit, that you're never going to be able to tabulate tabulate all the 30 crossing knots. But SnapPy has no problem computing the volume or any number of other invariants, the twisted Alexander polynomial, whatever. So there are things much beyond what we could ever tabulate that we can study. And so what I'd like to do is sort of explore the space of three manifolds by asking what a random one is. And so Bill and I did some work on this, in particular sort of a model of random manifold. And to keep within my mandate of this talk, just let me show you how to create those manifolds here in SnapPy. So our idea was you should take, to make the analogy with Danny's talk, this is the few generators model of a random manifold. I mean, you don't really have a choice, but that is the thing that it's closest to what he was talking about. And so in particular, you just fix a genus of a surface. Let me just do genus 2 for the purposes of this talk. So I created a surface of genus 2. And I'm going to take two handle bodies of genus 2 and glue them together by a long word in the mapping class group of that surface. So this is genus 2 surface with the sort of standard 5 generators of its mapping class group. And I just picked a random word of length 100 in that mapping class. So I can ask it to build the Haggard splitting associated with this. I should say this is the component twister that was written by Saul Schleimer, Mark Bell, and Tracy Hall. So I have to just specify how I'm gluing on the two handles. Let me ignore that. Oh, that was not a hyperbolic manifold. Let me draw another random word. Whoops. There we go. So it's a theorem of Joseph Marr, one of the papers that I listed, is that for sufficiently long words, these manifolds are always hyperbolic. But it actually takes a while to get into that regime, as you can see. And you can also do things like build a random bundle. So the bundle has much more volume than the Haggard splitting. It's sort of what you expect. Igor Rivin had an interesting paper on the archive recently studying the property of random bundles in the sort of spirit of what Bill and I did. So for my very last trick, and then I will stop, is show you a feature that's not there yet, but will be soon, which is a particular model of random knots I've been studying with some of my students. That allows you to just create knots that are sort of arbitrarily complicated. And the model is not one that's been studied before exactly, although it's close to some of them. But it's something that comes close, we feel, to, give me something with more crossings. We feel comes close to the spirit of what it would be like to draw a knot from a, if you could tabulate all knots with 76 crossings, this is what they would look like. So I'll stop there. Thank you for your attention. Can I make this smooth? Yes, but I don't promise it's going to remain embedded. Oh, yeah, sorry. Maybe let's just talk afterwards. It's got a lot of steps. So.
Can I deal with infinite volume manifolds? Geometrically finite infinite volume?
Yeah, so geometrically finite infinite volume. So I've actually been playing around with that recently. So you can try to use this twister program to explore that. So what I've been doing is I've been taking so I have this manifold with, say, one genus, two boundary component. And I want to sort of move around in its deformation space. So what I do is I just attach random something to the other side. And that gives me this complete hyperbolic structure on that finite volume. And by doing that, you can kind of move around in the type deformation space. Now that's Kurt.
So I just want to share with you a fantasy I had. There was this tool is so fantastic. The amount of energy that's gone into it is comparable to that goes into the construction of a NASA space probe. And as many of you may know, there was a NASA space probe launched in 1980, and nobody can read the tapes anymore that have the manual for controlling it, even though it still has fuel and it's within radio range now. And I'm just wondering how you will guarantee the longevity of this incredible tool.
Well, the way we should guarantee the longevity is for more people to join us in working on this program. We would certainly appreciate a bunch of minions. The source code is online. You can get a copy of the source code. You can work on it. And yeah, I mean, I didn't say anything about the history. This program, I mean, it was originally something that was written by Jeff Weeks alone in the 90s. It was a program that worked on Macintosh computers. And due to, passage of time, it no longer runs on any computer you can buy today. And that's been true for a little while. This is something we rewrote, basically. The interface, the core library is the same. It's the same code, but some additions. But and I think it's a fundamental problem, actually. I'm going to be, the Institute ICERM at Brown is thinking about trying to come up with some, sort of like software journal or something like that to try to address these issues. And I think they're hard issues. I don't really know what's the right way. I mean, you might think the computer scientists would have solved this problem, but it's really only recently that they've started trying to kind of archive the programs that go with, say, conference proceedings. They now have sections that are called computational artifacts. The problem is, computers change and then it doesn't work, and then, the code's out there and many people use it. If it doesn't work, please let Mark or I know, and we'll try to fix it. But I don't have a good answer to that. Yes?
Can you specify a manifold by giving a presentation in PSL2C for its group?
Yeah, so his question is, what if I had a bunch of matrices that I knew would correspond to the holonomy of a hyperbolic manifold? Could I use SnapPy to, say, recover, for example, a triangulation, compute its homology? Yes. So in fact, you can start. So what I showed you was taking a triangulation and making a Dirichlet domain. If you start with the matrices, you can feed them directly into the Dirichlet domain and ask it to feed the matrices in. It'll find the Dirichlet domain, and you can ask it to triangulate that. Yes, it can. Yes, Franz? What? Surface subgroups. It does not have any real facilities to deal with that. I mean, you can certainly take these things and feed them into some normal surface program like Regina. You can run both Regina and SnapPy inside of Sage, for example, and then find, say, an incompressible surface. But we don't really have any tools for then taking that and looking at the developing map. I mean, I've played with a few examples, but there's nothing systematic that's provided. That would be nice. Yes?
You didn't want to get the invariant trace field stuff, but maybe this will give you an opening. Did you find an example of a cusp and a closed hyperbolic manifold, non-arithmetic with the same volume?
Oh, non-arithmetic with the same volume. You wouldn't, I mean, you could look for such a thing, and you could sort of convince yourself it was true, but if it wasn't arithmetic, you could never prove it. Right? I mean, somehow the only reason we can say two manifolds are the same, they're not commensurable, is because of some volume formula. Yes?
You had some links earlier, and then you said what the short GD6, how long they were. Can you draw them?
Oh, so he's asking, could I draw the, like, could I go to that picture of 942 and like draw with, yeah, and so you can. In fact, I almost did that as part of my demonstration. It's just, I got it wrong like half the time, and so I cut it. But yes, you can do that. It's a good exercise. You can bring up 42, bring up its link thing. It kind of goes around on the outside. It's not really that short. It took me a while to find. But yeah, you can definitely do that. Yes, middle. Oh, the Whitehead link? Well, let me just point you to the page of, since we are way over time, the page here of the documentation which shows you how to find the trace field of some example. I should warn you, this code is not as well developed as what comes with Snap. It's somewhat preliminary. It doesn't work on examples. It really should. Again, more minions, please.
I think we should stop the questions so that people can ask individually. There are people wanting to leave, so we'll move on.
Yes.